Log on, tune in, find out. Another good idea from Cambridge.
Talk of the morning before a coffee break is Sebastien Rouquette, who is going to give us yet another domain area. Thank you very much.
The main variety of this morning and probably of the week. So I'm going to talk about welding today, so it is quite different what we have heard or talked all the whole week. So I'm coming from Montpellier. So if somebody doesn't know where is Montpellier, it is where? Here. So it is where is located my laboratory, but the facilities for the welding are at the Université de Nîmes, and it is also where I teach some welding course and non-destructive testing and design of experiment. So this is how I have organized my talk today. So first of all, I will present the welding, so the Gas Tungsten Arc Welding process, because I'm not quite sure that everybody knows what is the welding. Welding probably yes, but this special one no. Then I will introduce the context of this work. It is a preliminary work I gave firstly to my PhD student to be introduced to the inverse problem. Then I will talk about the physics involved in this process, because it is a highly coupled process and it is important to understand what we are talking about. Then we state a first easy, simple heat transfer and hydrodynamic model in this simulation, and I will talk about our main problem about in this inverse problem. I will go into it in this part, and then I will conclude. So what is a welding process? Basically, it is a process that will assemble two metallic parts by welding one part of a small part of a workpiece. Basically, you have two workpieces, two plates together, and you are welding along the border of the plate, and you melt this part. So in arc welding, and especially gas tungsten arc welding, you're using an electrical arc to melt the metallic workpiece. So here you can see an electrical arc. It is recorded by a high-speed camera. I don't remember the frequency, it's probably around 8,000 Hertz. And we use some UV filter to cut the electrical arc. Even if you have some small part of the electrical arc, I don't know if you have seen some welding process, it is impossible to see, and it is quite dangerous and harmful because we have lots of ultraviolet rays coming from the electrical arc. And you can see quickly the weld pool moving due to the arc pressure. Here we have an electrode in tungsten, generally in gas tungsten arc welding, and a gaseous is used to ionize and help to stabilize the electrical arc, because the atmosphere is quite not very good electrical conductor. So we use generally some argon or helium to enhance the electric conductivity in the surroundings and that stabilize the electrical arc, but also we use a second thing to protect the welding pool and the surface that is hit from the oxidation. So this environment is quite severe, so you have some electrical arc of the plasma rays in the UV range. You have a temperature of the plasma around 10 to 20,000 degrees Celsius. If you weld some steel, the temperature is higher than 1,500 degrees in the welding zone, welding pool. And we have some high welding intensity, so over 3 ampere, it is harmful for the human body. So the context. In the welding industry, what they want, it is to improve the joint quality, so I mean the mechanical properties. Because when you are heating a material, you are sometimes losing some properties of the material, so we want to improve that. Another thing is you are heating a material, so you have lots of deformation. We want to prevent this or to reduce this deformation. And another topic is the real-time detection of the defect during the welding procedure. So I won't talk about this one. We'll mainly talk about the first point. So due to the severe welding condition, it is quite difficult to do some measurement and to be able to say, okay, the quality is fine, we can follow the process. So one solution is to do some welding simulation. So now, you know, the computing is quite, the power of the computing is quite important, and we can do some complex simulation. Multi-physics one, not only taking into account, you know, the heat transfer problem or the thermomechanical problem to get the deformation, something else. So what we aim to do it is to simulate basically the process in heat transfer and fluid flow thinking to get the well pool shape, because this one is one of the key in the, I would say, quality of join here, because the form of the shape of this well pool will modify the temperature field through the workpiece, but also it will change microstructure properties. Another thing, it will play an important role on the deformation. So that means when you weld, you want a thin, narrow joint and a deep one, if possible, and you have less deformation. So first of all, I will describe briefly all the physical involved in the welding process. So in the gas tungsten arc welding, you have the electrode, and you initiate the electrical arc between the workpiece and the electrode. So you have an electromagnetism problem and fluid flow in the plasma, and I won't talk about this one. And if you take into account only the workpiece, you will have a well pool when you are over that fusion temperature for the material. And in this well pool, you have many forces. The first one is the Joule effect, so heating. You have some Lorentz force due to the electromagnetism problem and the field induced by the electric current inside. You have also some convection, or called buoyancy force. That means the material, when you heat a fluid, is going up, and you have some motion of the fluid due to these things. Basically, I will go into it a bit later. So, and we have also the Marangoni force. So this force acts on the top surface of the well pool, and it is quite important because it will push the fluid towards the from the center towards the border of the well pool. So we have some motion. So if I go a bit into the detail of this force in the well pool, the first one was the buoyancy force. So here on the top of the well pool, the liquid is water, then on the side of the well pool. So finally, you have some this sort of motion of the fluid. So here, the fluid is going away from the center to the border and going down the fluid. It will play a minor role in this welding process. Then another important force is the surface tension or Marangoni effect. So this one is applied along the surface, and it will depend on the gradient of temperature along the surface. And if this surface tension force is positive, this coefficient, negative, you will have a motion like this, I mean, along the surface, away from the center. If this one is negative, positive, sorry, the coefficient, it will be the opposite. It will go down to the center, and it will go deeply in the weld. So you will have a better penetration. Other force, so I will add this. So this is a scale about the dominant force according to welding intensity. So you don't see here, but it is 200 ampere. So basically, this one are dominant below the 200 amperes, and this one are dominant greater than 200 amperes. So this one is due, this force, the Lorentz force, is due to electromagnetic field. So it will cause a deeper weld pool. And the last one is the air pressure. So you have a pressure due to the plasma, and it is acting on the well pool and try to enlarge the well pool. So basically what we prefer is this sort of force, Lorentz, because we will get a deeper, well pool, and probably a narrow one. So first of all, the stated model is quite simple, I will say. Basically, we are using only heat transfer model or thermomechanical one to get the deformation. So we want to here to know the well pool shape. So we need to use a fluid flow model with the heat transfer. So as I said, it is a very preliminary study. So we are doing a static test welding, not a real one like in the industry, not two plates weld together, because it is too complex to study. We have a contact between two plates, and we cannot. So it is a cylinder, and you have a torch on the top, and we are heating this cylinder to create this weld pool shape. So we decided to work in axisymmetric geometry, so it simplifies the model, and also in time of computing. We divide this one in two parts. This one is purely solid, where we will be solve only the transfer problem, and this one is fluid and in-transfer. It will be a fluid domain where we solve the fluid flow and also the transfer. Here we apply a condition that if we are under the fusion temperature, this solid has a high viscosity, so that means the motion is unprevent to appear. And when we reach the temperature of solidification, the solid, yes, the fusion temperature, exactly the solidus temperature, when the solid is starting to melt, we decrease this velocity, viscosity to get a normal one. And this value is reached when we are reaching the liquidus temperature. That means when the fluid is totally liquid. So we are working under a welding intensity of 200 amperes, so we can neglect the Lorentz force and the arc pressure for the moment. And the heat flux, so coming from the electrical arcs, is supposed to have a Gaussian distribution. And the material is just carbon steel S235, classic steel used in the bridge manufacturing steel bridge. So basically, I will summarize quickly the model we have stated. So on the top, you have this heat flux obeying to a Gaussian distribution. Yes, I forgot to start with. So the domain, as I said, where we solve the Navier-Stokes equation and the heat transfer problem. The one where we solve the solid one, where we solve only the heat transfer problem. Then we apply, in case of heat transfer problem, this load or heat flux on the surface. We have some boundary condition around for the heat transfer, both convective and radiative, so some heat loss. And then one of the most important for our Navier-Stokes problem is the surface tension effect, and where we take into account this Marangoni effect, and so it will affect the motion of the fluid. So this model is a PDE1, where we have a heat transfer to solve with associated boundary condition, the Navier-Stokes, with also its boundary condition. The heat flux is described as follows, so this Gaussian function, where we can use the welding, the current welding set parameters, I mean the welding tension and welding intensity. We have in our facility a welding bench where we have instrument this bench and we can measure the welding parameters. So that means welding tension and intensity. And also we can record some image, some movie from the weld pool on the surface that will give us some information on how it behaves. And that's why you can use this data inside this formulation. And the two parameters we'll discuss later are this Gaussian reduced, so the distribution of Gaussian, and here this coefficient eta, the efficiency of the process. These one are not well known from the process. It is known, I would say, that experimentally, yes, you feed this data to this value. Basically in TIG, Gas Tungsten Arc Welding, we say it is 0.7, and here you will take something between a radius of 2 to 3 millimeters. It fits quite well, so it's fine. I forgot to say something. Basically, in the welding industry, when you set up a welding process, you have some standards. What I mean is they have a welding knowledge, how to weld these two metallic parts. So it is a thicker of 10 millimeters. So you will use a range of, for example, 100 to 200 ampere. So it is lower than that, 100 to 150 to weld it. After, I don't know if it is better to use 120 or 130 amperes. And the problem is, if you add more heat input inside, you can change the material properties. So what you want it is to optimize it and get a better value for this. So in the Navier-Stokes equation, sorry, it is quite the basic one, where we have add the buoyancy force. This term I said previously, where we take into account that the solid is not becoming fluid instantaneously, so we add a parameter inside. And the next thing is, yes, and the boundary condition on the top surface to take into account this Marangoni effect or the surface tension effect. So this coefficient need to be known quite accurately. In this study, I will take it, I said, to a constant value, but, and I didn't say something as well, this one depends on the temperature, but also in the composition of the metal of the steel, and mainly on the sulfur content. So if you don't know the sulfur content of the material, you are not able to simulate it. So it is not a question here, because this one can be characterized experimentally. So the other assumption, to simplify the problem, material density, basically all the other parameters are quite constant. So even it is not a linear problem, because all material properties are varying with temperature, I consider it as constant to gain some time in the computation. That's it. Later we'll do it with good, I said, proper assumption. So the surface tension in this case is taken to minus 3 to this negative value, normally we should expect in the simulation a large whirlpool, and the motion of the fluid is going along the surface away from the center. We have used the FIAN software, commercial one, console. I know quite well this one, that's why I use it. And also because we have a link with MATLAB. So that means I can work with console and MATLAB at the same time for my optimization loop later. So the mesh grid is given here. So finally the computation time is not too bad, I would say. We have about 18,000 degrees of freedom, and it takes about 15 minutes to simulate 7 seconds. So for real-time simulation, real-time also control the process, it is not good. That's why I say it is not the purpose today. Here it is the heat flux. I am froze. I mean the Gaussian distribution according to the time. So this is in the center of the cylinder. I didn't take the experimental data because they are quite disturbed at the beginning, and I wanted something quite straightforward to test this procedure. So if you know all the parameters quite well, you can do a simulation without any problem, and you get some result. So here it is, this cartoon depicts basically the temperature field at different times. So this one 1.7, we have applied the load heat on the top surface, and as the thermal conductivity is equal in all the direction, you have a sort of quite normal quadratic propagation or something else, I don't know. So it is after different step time, and we can see that around here 3.5 seconds we have start to melt on the top of the surface. Well, this is just to show you not very, even some measurement at different points of the geometry. So not in the whirlpool size, because I won't be able to do it later, just around to show you the evolution of the temperature. And this one is the solidus temperature when the solid is starting to melt. So here it is what we expected in this modeling. So basically we use this negative coefficient for the surface tension, and the motion of the fluid is occurring along the top surface, turning here and then going slowly to the center, decreasing the velocity, and it is faster, the velocity is higher in this area. Now if I change, for example, the coefficient, it becomes positive. If we have a high sulfur content, we can get this sort of shape. So it will affect a lot the whirlpool size, and also the temperature field inside. So as I said, if you have very well all the parameters, you don't have any problem, you can do a simulation. One problem is we cannot really assess the heat flux on the top surface. So I described it with a Gaussian function with not only two parameters, but two parameters are not known. And what I want to do it is to identify this parameter, to estimate it with an inverse method. So what kind of information I have? Basically, I will be able to do some temperature measurement within the material. And what I want to do is where I have to do this measurement to get more relevant information to do this estimation. Oh, affect the temperature, I forgot. So this is my problematic. I don't know quite correctly eta, so the efficiency of the process, and the Gaussian beam radius. I want to estimate these two parameters, so I define this as you have called, I call that criterion function or cost function, but also the objective function. It is the difference between the calculated temperature in the domain and the measured one. And the goal is to minimize this function by finding this set of vectors. The method I have chosen is the Levenberg-Marquardt method because we have only two parameters, so it's quite easy and straightforward to set up. So here I sum up the method. Basically you have core modeling, so my heat transfer with fluid flow with some parameters inside, and the unknown one are P. So I calculate my data, I compare here to the measured one, and I can compute the criterion. When I start the first iteration of the process, I'm going through this loop. So I hope normally the criterion is decreasing, and I use a Levenberg-Marquardt method. It is here. It is basically here the Levenberg-Marquardt method, I would say. I define two sensitivity problems related to the two coefficients, eta and radius I want to estimate, to make this sensitivity matrix. This sensitivity matrix is the key, the key of this method, or success of this method. And then the new estimate, so new set of parameters estimate following this formula, where you have G is the sensitivity matrix. I don't know what is omega. And here you will find the difference between the measured, calculated measured temperatures. And then we will restart the procedure until you get the criterion reach a value you have found or very low. If this criterion is increasing instead of decreasing, you change the value of the number backward value by increasing it by 10. And it is decreasing, you divide it by 10. So I said the building of the sensitivity matrix is quite crucial, and you need to define the sensitivity problem to compute it. So you have several methods to compute the sensitivity coefficient, and the easiest one I took was a forward difference finite scheme to estimate the sensitivity of this coefficient. So this is the definition of the sensitivity. That means the temperature derived to the look coefficient estimate, and I use a small perturbation in my temperature field on the unknown coefficient, and I just do this forward difference basically, and I use an epsilon coefficient equal to 0.05. So what I'm looking for now, I need in the sensitivity matrix that the coefficients are totally linearly independent. Also, I need they are relevant to make this inverse problem to solve it. So how can I do? So basically, I will say I will do first a sensitivity analysis. So again, these cartoons are depicting the field of the efficiency sensitivity value, or the ISO value for the efficiency related to the sensitivity problem to efficiency. So you can see that these values are quite high, but that don't really is enough to say if this is fine or not. You can see that the sensitive area are this one here at the beginning of the simulation. Then when you are at the times greater than 2 seconds, this area is changing a little bit on this side. So the sensitivity problem is really related to the forward one physically. So because you have increased this efficiency value by an epsilon coefficient, finally I increase the heat input and I change the size of the well pool. I mean the wide of the well pool here. That's why you can see a difference. So this is the part of interest to make some measurement for me. It is the same for the sensitivity values according to the Gaussian radius, and the most interesting part to make some measurement is here, located on the axis symmetry. And you can see also that the most important sensitivity is located here. Okay, so far I said, okay, my area where I need to make some measurement is here, globally. But it's pretty tough to say they are independent. So I will use some normalized sensitivity, and it is defined as like this. I forgot, it is a mistake. For me, G is a sensitivity matrix, the sensitivity related to a coefficient, and I multiply by the value of the coefficient. Finally, I can compare all the sensitivity in the same unit. So when I do that, and I do this ratio, I compare for the 5 point I've said, this is a 5 point where I measure temperature, I said, so this is the coordinates. And for me, the most interesting point where the ratio is quite varying between the two sensitivities are these 3 ones, so the 3 first. So it is this point where it seems we are quite independent, and I can perform the estimation in this method and build my sensitivity matrix. So I will use this point in the next to estimate my parameters. So quickly, it is how I implement this procedure in MATLAB by using COMSOL. And here, this COMSOL problem, you can save it in MATLAB form. So after you can use it in MATLAB to export data, send the parameter you want to estimate, and make a computation all the time. It remembers just the loop I showed before. I studied only 2 cases. Normally I said I will use also some experimental data, but we didn't do any measurement at the moment. So the first case is solved with exact data, so it is not quite difficult. And the second one, I used some noised input data, but it was following a normal law with a standard deviation of 5% of the current temperature. So the normal data, I mean, without noise, has a full line, and this one, the second one, is one noise I will use in this estimation. So what happens if I do that? Here it is the criterion of a cost function. So the difference, quadratic difference between the temperature and the measured one, you can see that for the exact case, it is decreasing to a very low value, so that means I have well identified my parameters. And for noise data, it is stabilizing just before, equals to the noise. You can see the first parameter identified, the TIG efficiency. It was set to 0.7. The final, the real value was 0.7, sorry, and it was set to 0.1, the initial guess. So in both cases, it is quite fun. The accuracy is quite good, so we don't really have any problem. Exactly the same for the estimate Gaussian radius. It was set, the initial guess, to 20 millimeters, and we were looking for a value of 3 millimeters. So in both cases, it was, I would say, quite okay. Now we can also do some other computation, I mean, on the accuracy of the data. From the sensitivity matrix, you can compute the Hessian, and from this Hessian, you can say that the inverse of Hessian is also equal to the covariance matrix, and you can evaluate also the accuracy on the parameters. And just something I wanted to say, if you do that, you look that in both cases, you have quite a good result, but basically, when you add some errors, you have an interval of inaccuracy for this coefficient quite high, but even if I got the good value at the end. So effectively, I would say with three points of measurement, three data, input data, and only two parameters to identify, it was quite straightforward to do it. I mean, after really, when you apply it to the experimental case, the model is sometimes not exactly the same, so you have some errors. And I didn't try to do this sort of test, trying another sort of modeling to see the impact of error on the modeling of the process, because I don't take into account the electromagnetism and many things, and also because all the parameters are temperature dependent. So we will do that in the future. So as I said, it was a preliminary study, so we did these things, but what we aim to do later, it is not to impose basically heat flux function like a Gaussian, but to discretize it on all the whole surface and to find this data on different points to get to not impose just the function to find. So that will say we will have a greater number of unknown to estimate, and I'm planning, already almost did that, to use the adjoint, the conjugate gradient method to use it, estimate this heat flux, but a surface one, and to improve the modeling as well, because it is the goal of the aim of this PhD at the end to do a full, I would say, multi-physics modeling. I mean, electromagnetism, heat fluid flow, and heat transfer, and for high intensity. Thank you.
Do you have any questions for Sebastien? Burning questions? Well, I wanted to ask you, you have quite a lot of parameters, so you didn't seem to be using any regularization explicitly.
No.
So I was wondering, perhaps other people know this, but is the Levenberg marker algorithm is equivalent to imposing zeroth order Tikhonov, is it not? Is that right? Yeah, zeroth order Tikhonov.
Ah, yes.
Yeah. And in the Bayesian interpretation, that's the same thing as assuming that your data looks like white noise, which may or may not be correct. But I just, yeah.
Basically, I never use this Tikhonov regularization method, but I don't know.
Right.
Because I was not used to do that. And I know sometimes the problem we have is not, I said some parameters like the material properties are quite easy to know. I mean, you can do some experiment to find them. But the problem is more the modeling you're doing, the initial modeling. Here it's the fluid flow, heat transfer, and if this one is really wrong, you won't see the data, or you will have a huge inaccuracy. But I never use this regularization method to try to improve it or not. So it is.
And how easy will it be to implement adjoints in the COMSOL sort of framework?
I use exactly the same way. Basically, in COMSOL, I set up a forward problem. Now, it is quite long to explain. I would say, no, I'm joking. I mean, first you have to establish the adjoint equation, and then it is a bit straightforward like the heat transfer problem. It is also a parabolic equation, PDE, you have IDL, and you can set up in the console like a heat transfer problem or a fluid flow problem.
So you'll have to set up the adjoint equation
Yes.
analytically and
Yes.
then solve it in COMSOL. So that's
Solve
rather
it
like
in
the
COMSOL.
weather forecasting people do it that way.
Yes.
Whereas the oil people discretize it and then work out the adjoint.
Okay, now I
is
enter it in
fine.
console, I save it in the file, and then I can take my data as I want. This is how I do it.
Anybody else want to? Right, so let's thank Sebastien once more.
Thank you very much. Happy console.